So how many of you are aware of a system in India that is popular in called salami method? Like when people try and sell a asset, typically a house or a shop, uh, in those kind of thing, what happens is somebody is owner of a say shop, say they will come and somebody want to interested in taking that shop, they'll say, okay, I'll pay you, if the actual value of the shop is say 35 lakh rupees, he'll say, I'll pay you say 15 lakh rupees per upfront, and then I'll pay you say 5,000 rupees per month in perpetuity. Means I'll keep paying. Every month I will pay 5,000 rupees as a sort of a rent, and 15 lakh rupees per on upfront. And this is actually a perfectly legal uh, setup that happens. Now, the question that I have, are you aware of this kind of system? It's called salami method. Salami, like the amount that you are paying, like let's say 15 lakh rupees or something, is called salami. Like, any idea? Anybody have any idea? No? All right. So um, this is quite popular. Okay, there is one question. Yeah, Pragya, you want to say something?
Also, you asked if we knew about
Okay,
it.
got it. So yeah, so this is the method clear? This is typically popular in the old economic style. Uh, but what happens? How you decide what should be the, so in proper quantitative finance, they call it, there is a particular term is there called bond in perpetuity. Perpetuity.
Sir, is it somehow related to those government bonds where
Yeah.
you can keep on giving a certain amount for infinite number of time or number
Yeah,
of years?
yeah, not infinite times. Generally, government bonds are always time bounded. In India, most of the government bonds are 10-year bond. That is the maximum. Some of the state government nowadays are issuing 15 years bond and 20 years bond. But I mean, out of 1,000 bonds that are uh, generated, probably 900 of them are only 10 years bond. So this is same basically. So not only government issue the bonds, um, sometimes really big firms like Reliance, Tata's, they also issue the bond in the bond market. There is a unfortunately, Indian bond market is not very well organized and very big, unfortunate, because I really believe that uh, a sign of a well-formed economy is its bond market. People think like, sign of a well-formed economy is its share market. No, if you go to United States, if you look into the size of the share market of United States and the size of the uh, bond market of the United States, you will see the size is maybe 10 times bigger for bond market than the share market. Same thing with the UK, same thing with the Germany, same thing with the most developed nations in the world. Whereas in India, it's a ulta. Our bond market is fairly small. One reason, it's a high entry bar. The way regulator regulates, not many people get allowed to get into that. I mean, if you want to buy a bond, you minimum have to have 10 crore rupees in your pocket to get into there in order to bid for a bond. So you can see that only the institutional investors are allowed. If a single bid is only 10 crore rupees and you are not allowed to uh, bid below 10 crore rupees, that means basically you are saying any chota mota you get out, and we will just entertain only the big ones. Who can afford? Only Reliance and Ambani's and Birlas can afford. So bond market is pretty much out of India's context. And then where people go, so people like you, me, we go to the State Bank of India. We put our few lakh rupees in the fixed deposit and they gave us whatever throwaway price. And this is how our, that's how rigged basically Indian financial system is the most corrupt in my opinion. I am saying it on record because literally we are not allowed to go into the bond market. Anyway, so let me, so bond in perpetuity is a special kind of uh, bond. So let me just say, give you the idea how it works. So basically it's saying that suppose on year, and let me, so year 0, 1, 2, 3, okay. On year, it's saying, the bond is saying on year 1, suppose you will get uh, say 5 rupees. I'm just keeping it simple, okay. Year 2 you will get a 5 rupees. Year 3 you will get a 5 rupees. Sorry. In this way you will keep getting 5 rupees every year. I'll keep giving you 5 rupees, okay. And question is how much, if I, if you, and I'm giving you in writing that every year you will get a 5 rupees from me, then yeah, and I'll give you this in writing in a paper. But in order to get this paper, you have to give me, and how much I should, basically you have to give me something. So people say, okay, I'll give you my place where you can sit and do your business. Then he'll say that how much I should pay you upfront here. And that is typically called the salami. And can we figure out what would be the value of this? Okay. Can anybody guess? So year 0 is today. Year 1 is 1 year from today. Year 2 is 2 years from today. Okay. So one way of calculating this value of that area is of, so and typical bond will, this is a typical bond in perpetuity, and typical bond will be like this. Typical, which is typically in finite terms. So year 0, 1, 2, 3, maybe 10 years or something. I'll write n could be 10, 15, 20. Sometimes it's 1 also. 1 typically a 1, 2, 3, 5, 7, 10, 15, 20. These are the typical number for which the uh, bond are being issued. But the most popular is any 10 years bond. And the value that you're going to get is like on the end of the first year, you will get 5 rupees. End of the second year, you will get 5 rupees. On the end of the third year, you will get 5 rupees. End of the nth year, you will get 5 rupees plus 100 rupees. Typically, it is the called par value or the face value. Par value or known as face value. Okay. Question is, so I am saying, suppose I am the one who is issuing the bond. Okay. And Shinjini is one who is going to buy this from me. So what I'm doing on a piece of paper, this is suppose the piece of paper, I am writing this. These are the payments I will make to Shinjini and for the next 10 years or nth year. Okay. Now tell me, how can I, if I have to give this piece of paper to Shinjini, Shinjini should pay me something. That will be so these are the value that Shinjini is, if that value says suppose some X amount, that will be at this moment Shinjini will pay to me again, and I will give her this piece of paper, and I'm legally binded to pay her this 5 rupees, 5 rupees, 5 rupees, 5 rupees, and 100 rupees on the last year. This is typical bonds. We have to figure out what is the value of X. Can anybody tell me what will be the value of X? How we approach it?
It will depend upon the value of n.
Mm-hmm.
So basically, we are giving 5 rupees n times. So in total, we are giving 5 into n plus the par value, which is 100.
Correct.
And that should be at least x.
Right. So you are saying that X should be at least 5n plus 100, right?
Yes.
All of you agree with her?
Sharjul is saying something on the chat box.
Okay, correct. Shairul is saying discounted price of the coupon. So yes, I have not introduced a jargon. These are typically called, these 5 rupees are things that I am paying you. These are typically called coupon. There is a history behind it, why it is called coupon, but I will tell you some other day what is the history of uh, calling this small amount as coupon. But and the plus discounted price per value. Okay, what Shairul is saying is right. We have to discount the price, and I'm asked Shairul, can you explain uh, what you mean by discounted price to the class?
Like we have to like ask for the amount such that if we add the interest rate, the amount will be equal to $5, like $5 or 5 rupees in that particular amount at particular amount of time
Correct. So,
for
okay,
every year
yes,
separately,
yes. So
and add all of
basically,
them.
correct. Yeah. So basically, let me explain you what is it mean. So 5 rupees is, I don't have to pay 5 rupees today. I have to pay 5 rupees 1 year from today. So what I will do, I will probably put maybe I'll ask one easy way to solve. For me, I have to pay 5 rupees from today. So what I can do is I can ask, I would look into that. Okay, says what is the fixed deposit rate in SBI? SBI is say paying 5%. So that means 5 paisa in 1 rupee. So 25 paisa. If I put about 4 point maybe 75 paisa in SBI, it is not exactly 4.75 paisa in SBI today. Today I will put 4.75 paisa maybe. Then after 1 year, it will become 5 rupees, and I'll pay 5 rupees uh, to Shinjini. Okay. Similarly, I will pay maybe I'll put 4.5 rupees around that in SBI, which after 2 years will come, will, you know, mature as 5 rupees. And again, I'll pay that 5 rupees to Shinjini. In that way, I'll keep doing it. Okay. So what I will do is basically this. So what I mean by this, basically, I am saying this 5 rupees, what is the uh, today's value of this 5 rupees? This 5 rupee is not today's value. Today, its value might be little less because I put the little less money. After 1 year, it will become 5 years. I put little more less money in SBI, and 2 years time, it will become 5 rupees. So my question is, so what we can do is basically it will be 5 into 1 plus some r. That will be the amount I will put in the SBI. In here, I will put 5 into 1 plus r square. That will be the amount. So r will be some interest rate between 0 and 1. Okay. So for 5%, it will be 0.05. So for third year, it will be 5 by 1 plus r cube. In this way, we will keep doing 5 by 1 plus r to the power n and plus 100 by 1 plus r to the power n. Okay. So if I add that thing, it will be like 5 by 1 plus r plus 5 by 1 plus r square plus dot 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 5 by 1 plus r to the power n plus 100 by 1 plus r to the power n. Okay. So I can take 5 common, will be 1 plus r plus 1 plus r square plus dot 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 plus this to the power n plus 100 by 1 plus r to the power n. Okay. Now let's take n equal to 1. Suppose it's a 1-year bond. Okay. Suppose it's a 1-year bond. So basically, at the end of the first year, I will pay 105 rupees. That's all I am saying. Okay. If I give Sinjini is ready to buy this piece of paper from me, I'll be ready to pay 105 rupees at the end of the year. So that means basically 5 by 1 plus r plus 100 plus 1 plus r to the power 1 plus r. So it's basically 100 and yeah. So now you take say r equal to say 0.06. So can anybody tell me what will be the value? Can you just use your calculator or r to just, can you give me the value? So you just plug in and then it gives me the value.
65.625.
65 point.
Sorry.
No, I
There's a
don't know.
calculation error, yeah.
Yeah. There must be, it must be a little more
It is
than.
99.057.
Okay, very good. 99.057. Okay. So 99 point approximately 99 rupees 6 paisa. Correct? So basically that means if Shinjini should pay me 99 rupees 6 paisa today, then at the end of the year, I should pay her back 105 rupees. Okay. So that's how the bond, typical bond works. Typical bond works. Now comes to the bonds in perpetuity. So the how the bonds in perpetuity works. Am I writing the perpetuity? Probably right. I don't know. I'll check the spelling later. Okay. So basically, I'm saying that okay, I'll keep paying 5 rupees, 5 rupees, 5 rupees, dot dot dot. I'll keep paying. Okay. Every month I will keep, or every year say I'll keep paying this 5 rupees, 5 rupees, 5 rupees, 5 rupees. What will be the, this is the legal paper that I am saying I am selling to Shinjini. Okay. This is a legal paper I'm selling to Shinjini. Okay. That Shinjini, I'll pay you 5 rupees in perpetuity every month. I mean legally until I die. How much? So this is year 1, this is year 2, this is year 3, and in perpetuity. So today is year 0. How much Shinjini should pay me for this legal paper? If Shinjini wants to buy this legal paper from me, how much Shinjini should pay me for this legal paper? How we should evaluate this?
We need n tends to infinity for the previous series.
Exactly. Very good. Very good. So what I will do, I will just say 5 by 1 plus r plus 5 by 1 plus r square plus dot 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 basically. Okay. So can anybody solve this series? So always I can say that a equal to 1 over 1 plus r. R is typically between 0 and 1. So that makes a to be between 0 and 1. Okay. So we can write it as a plus a square plus a cube plus dot dot dot, right? So if I take a common, then it is a 1 plus a plus a square plus sum of GP series, right? Now class 12 stuff. And what is the what is the where it converges, this series?
1 by 1 minus a.
Very good. So 5a by 1 minus a. And then I will replace the a by 1 plus r. 5 into 1 by 1 plus r, 1 minus 1 by 1 plus r. So basically 5 by 1 plus r. This is 1 plus r minus 1 by 1 plus r. So this will be 5 by 1 plus r. 1 plus r by r. So this cancels. Am I making, I think I'm making a mistake, you know?
No, sir, it is correct.
Hmm.
But sir, what about the par value? Will it tend to 0?
No, I'm not, I have not considered the par value or anything, but
Okay.
I'm just saying that, okay, I'm just, if I give you this thing, then how much it will be. So, okay. So this will be the, if R is say 0.06, so it will be some discounted value. I'll check. I think it looks little odd, maybe, but it looks like it's fine. Okay. In perpetuity. All right. So typically, bond in perpetuity will be like, it will be, bond in perpetuity really exist in a sense, only that salami method that happens. But also pricing that is a bit difficult, but that is one of the example where infinite series kind of comes a plays a role. Okay, next. Anybody have any questions, any doubts? Another example of infinite series in probability theory. Example of infinite series in probability. Okay, let's see how it works. So, um, let me write a, do you know, this is, just a minute. Hmm. So there is a sequence of numbers. So basically, n is taking value 0, 1, 2, 3, and a of n is basically lambda to the power n by n factorial, which is taking these numbers. And my series is n is sum of uh, maybe n equal to 0 to k a n, which is say like 1 plus lambda plus lambda square by 2 factorial plus dot 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 plus lambda k by k factorial. If k goes to infinity, where where this series converges, do you know?
e to the power lambda.
Very good, very good. So it will converges to e to the power lambda. I'm not going to the proof or anything. I'm leaving it for the Professor Kavita if she wants to do it. Now I am doing one thing. I am going to, so I have this basically n 0, 1, 2, 3, dot, dot, dot. And then essentially I have this a of n, which is a of n is basically lambda to the power n by n factorial. Okay. So I have basically 1, then lambda square by 2 factorial, then lambda cube by 3 factorial in this way. Then what I am finding that if I keep adding these numbers, eventually it will converges to e to the power lambda. This sum of infinite series will converge to e to the power lambda. That interesting. What I can do, I can now define a new sequence where I divide an by e to the power lambda. Do you understand what I'm saying? I'm dividing this, I'm defining this p of n as a of n by e to the power lambda. So I can write it as e to the power minus lambda to the power n by n factorial. So that means essentially this is what we have, e to the power minus lambda into e to the power minus lambda, e to the power minus lambda square by 2 factorial, e to the power minus lambda cube by 3 factorial. So can you now tell me where this is also infinite series. All I have done, just divide this a n series by e to the power minus lambda. Can you tell me where it will converge? One. Avik is saying it's 1. Yes. So basically, my p of n, each of them essentially is a value between 0 and 1. And if I add them up from 1, 0 to infinity, it will be 1. This kind of particular infinite series is known as probability mass function. Probability mass function. It has to satisfy two conditions. One, it is between 0 and 1, and we are How we do that? We take a series, we look into, okay, series is converging to this point, this guy. If we get a converging series, we can convert into a probability series by dividing each component with the value where it is converging. So what I did, I just divide each component of the AN series by e to the power lambda. Okay. Now, just a minute, guys. Okay. So in probability theory, if you get a sequence of, if you get any such sequence, is typically called kernel. So AN is known as kernel or kernel function. Sometimes it's called kernel function. If a sequence of kernel converges to, like, some big numbers, some finite numbers, then you just divide that sequence by that, what you will get a probability sequence. This is the trick that typically probabilists use from the real analysis. So now we can figure out, you can build your own probability mass function. If you want to build your probability mass function, you want to define. So this probability mass function is called Poisson distribution, right? So this is typically known as probability mass function, Poisson probability or Poisson distribution. Okay. But the trick is basically you find a sequence of numbers, the sum of that sequence of numbers, if it is an infinite sequence, if it converges to a number, if it converges to a finite number, you divide all components of that thing by this thing, and then this will give you the probability mass function, and AN is typically called the kernel function of the probability mass function. Okay, so this is another application of infinite series in probability theory, and that is how probabilists define. If they find that, okay, we did study we did study binomial, we did study Poisson, we did study negative binomial. Maybe that's it. That is where typical probability class will stop. But as a data scientist, when you will go into the field and you work with different kinds of models or different kinds of data rather, it might happen that you face a data which does not fit into neither binomial, Poisson, negative binomial, anywhere. Then what you do? One possible way out is you start exploring your calculus book, you figure out an infinite series which might be very versatile. Check if that infinite series is a convergent series. Turns out that infinite series is indeed a convergent series. Then what you do? You divide that infinite series with the value where it is converging. You define your own probability mass function and try to fit that newly defined, you can name that probability mass function after you, and fit it against your data. If it turns out to be doing better than binomial, Poisson, or the negative binomial, you can publish it. So that is one of the application of infinite series. in probability theory. Any question? Okay. I'll do a couple of problems and then we will. So this problem I'm going to do from Lang's book. Page 460, theorem 7.1. So this is one of the very nice expansion, theorem that binomial theorem, which is known as a binomial theorem, is a nice example of application of Taylor's formula. Okay, so it says that let n be a positive integer and x is not equal to -1. Then 1 plus x to the power s, you can expand it as 1 plus s times x plus s into s minus 1 by 2 factorial plus s into s minus 1 times s minus 2 divided by 3 factorial x to the power 3 dot 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 s into s minus 1 s minus 2 s minus n plus 1 n factorial okay. This is a nice example of binomial theorem, and where the proof uses basically Taylor's formula to prove this result. Now, sorry, in fact, the Poisson probability model, or the Poisson model that you have just seen, the e to the power lambda equal to that series, that is also another example of nice example of Taylor's formula. So would you like to discuss the proof or sketch of the proof, or you want to uh, okay, let me just quickly discuss the little bit of the sketch of the proof, and then we will move on to maybe another couple of examples. Okay. All right. Let f x equal to plus x to the power s. So what we can do is we can calculate these derivatives, which is s into 1 plus x to the power s minus 1 if 2x equal to s into s minus 1 plus x power s minus 2. S minus k. Now, if you take this and then here you take f1 0, then what you will get? You will get essentially s, right? Then if you take this one, if 2 0, you get s into s minus 1. If you, in this case, sorry, this was key. In this case, it will be s into if k 0, it will be s into s minus 1 dot s minus k plus 1. Okay. So what we can do, we can basically our kth term of the Taylor formula will turn out to be f k 0 by k factorial. This is the kth term of the Taylor formula is s into s minus 1 dot s minus k plus 1 divided by k factorial. So the remainder term is, and there must be a remainder term Rn x, which is f n c x to the power n by n factorial. Now that c is typically a number between 0 and x. Okay, so yeah, so the whole thing now boils down to s into s minus 1 dot s minus n plus 1 divided by n factorial 1 plus c to the power s minus n x to the power n. Now, one without any detail, basically, all you have to show that if minus x is between minus and 1 and 1, basically a fraction with the sign as well in unit interval, then r n x, the remainder term, eventually goes to 0 as n goes to infinity. So I'm not going into the detailed proof of how Rnx goes to 0 or Rnx and that all those things. But that's the idea pretty much, that after few terms, the remainder term will be have no impact and we can almost zero impact. So this is one of the implementation of use case of Taylor formula in binomial expansion. One of the problem that I found very interesting, or application of this Taylor Taylor formula, is solving a limit. With this, I will stop and I'll take any question. Okay, we'll do this problem and it's almost we're ending. We move to the time limit of today's class. This is I'm taking from page 468 of Lang's book. So limit x goes to 0 cos x minus 1, very standard problem. Probably you guys have solved it many times. But here they proved it, and you can prove it in many ways. I mean, I'm not saying this is the way, but here in book they proved it using Taylor's expansion up to one term. That's it. So what they have done is very simple. Replace cos x by 1 minus x square by 2 plus r 4x. Now if you do that, that means basically cos x minus 1 by x square equal to minus x square by 2 plus r 4x by r4x. Yeah. And then by x square. And then basically it means you can write it as half plus r4x by x square. So since r4x is bounded by mod x to the power 4, you can show that. Then essentially it means as x goes to 0, this part goes to 0, and hence the limit half. So this is, I found interesting in a sense that it was a nice application of Taylor's formula to solve this limit. So I have seen other way of proving this problem as well. So it's not like you have to solve it in this way, just one application. Okay, with this I'll stop here. I think now it's time for today to uh, discuss questions, comments. Any questions, comments? Okay, I think then we can stop today's recording.